Right now, on a station circling 250 miles above your head, a crew is alive because a machine recycles 98 out of every 100 drops of water they breathe out, sweat, and use. That number sounds almost perfect. It is not. Scientists have calculated exactly what happens if that station, or any spacecraft like it, was cut off from Earth forever, and the answer is not what you think. It is not the air that fails first. It is not even close. Tonight, we trace the real countdown, system by system, body by body, until we reach the true number, the one almost nobody gets right, and what it quietly tells us about the planet we already call home. If a story like this, one that takes something we think we understand and quietly turns it inside out, is the kind of thing you enjoy drifting off to, it would mean a great deal if you tapped that like button and subscribed. Not for any big reason, just so more nights like this one can find their way to you. And for now, let your shoulders drop, get cozy, and let the rest of the world fade out. In 3, 2, 1, liftoff. Picture a spacecraft sealed shut. No windows that open. No airlock cycling unless someone chooses to cycle it. No radio call promising a supply ship in 6 weeks. Just a hull, a crew, and everything they will ever have already on board the moment the hatch closes. This is not science fiction. This is the question scientists have actually run the numbers on. If you took a spacecraft today, filled it with the most advanced life support technology humanity has ever built, sealed it, and asked it to keep people alive with absolutely nothing coming from the outside, how long would those people actually survive? Not in theory, not in a movie. In reality, using real engineering, real consumption rates, and real human biology. The answer involves multiple overlapping countdowns, each one ticking at its own pace, and almost none of them are the one most people guess first. To understand this, we do not need to imagine some distant future ship. We already have the closest thing to this scenario in orbit right now, 250 miles above your head, traveling at roughly 17,500 miles per hour, circling the planet once every 90 minutes. The International Space Station has been continuously occupied by human beings since November of the year 2000, which means that, as of now, people have been living and working aboard it for more than 25 years without a single day where the station has been empty. In that time, it has grown from a handful of connected modules into a structure roughly the size of a football field when you measure across its solar arrays. Pressurized volume large enough to walk through corridors and float between separate rooms, something closer to the interior space of a 6-bedroom house than the cramped capsule most people imagine when they picture a spacecraft. That scale matters because the life support systems on board were not built for a tiny capsule housing 1 or 2 people for a few days. They were built to support a crew of up to 7 people indefinitely, for years at a stretch, which is exactly the kind of system this thought experiment needs as its starting point. The station is, in essence, a prototype ark. It is the most sophisticated life support experiment ever conducted, and every system on board exists for one purpose: to take what would normally be waste on Earth and turn it back into something usable. Air that has been breathed, water that has been sweated, exhaled, and yes, urinated. All of it gets pulled back into the loop and pushed through machines designed to make it usable again. The station was never meant to be fully self-sufficient. Cargo ships arrive every few months, carrying fresh water, fresh food, replacement parts, and the things the loop cannot yet replace. But the loop itself, the part that already exists, the part that already works, is far closer to a closed system than most people realize. And that is exactly why this thought experiment matters. We are not asking what it would take to invent a survival ship from scratch. We are asking what happens if we simply cut the cord on the survival ship we have already built. The heart of this system has a name that sounds almost bureaucratic for something so important. It is called the Environmental Control and Life Support System, and it is the unglamorous machinery tucked behind panels and under floor grates that quietly performs one of the most remarkable engineering feats of the modern era. Its job is to manage four things simultaneously: the air the crew breathes, the water they drink and wash with, the food they eat, and the waste their bodies produce. On Earth, these four things are handled by an entire planet. Plants produce oxygen, rain cycles water through rivers and oceans and back into clouds. Soil and bacteria break down waste and return nutrients to the cycle. Humanity does not have to think about any of this, because the planet has been doing it for billions of years, at a scale so enormous that the inputs and outputs simply disappear into the background. A spacecraft has none of that scale. Every gram of water, every liter of oxygen, every calorie of food has to be accounted for, weighed, tracked, and either carried up from Earth or recovered from something the crew has already used once. There is no atmosphere to dilute mistakes. There is no ocean to absorb excess. There is only the loop, and whatever the loop cannot capture is gone forever. It helps, before going further, to separate two ideas that often get blurred together when people imagine a sealed spacecraft: the loop and the buffer. The loop is anything that recycles, anything that takes a used resource and turns it back into a usable one, like the water recovery system we are about to look at in detail. The buffer is anything that is simply stored, used once, and never replenished, like food, or like the spare parts that keep the loop's machinery running. A spacecraft's survival time is not determined by the loop alone, and it is not determined by the buffer alone. It is determined by how the buffer holds out against the small, unavoidable losses that even the best loop cannot fully close, and by how long the loop's own machinery can keep functioning before its piece of the buffer, the spare parts that keep it running, runs out too. Every system from this point forward fits into one of these two categories, and the most important systems, the ones that ultimately decide how this story ends, are the ones where the loop and the buffer are tied together in ways that are easy to overlook. Start with water, because water is where the most dramatic improvements have happened, and where the numbers are the most surprising. For most of the history of human spaceflight, water was simply carried up and used once. The early space shuttle missions and the early years of the space station treated water the way a camper treats a bottle of water. Drink it and it is gone. But starting in the 2009 year, NASA installed something called the Water Recovery System, and it changed the entire calculation for long-duration spaceflight. This system takes water vapor from the cabin air, condensation from the air conditioning units, and most importantly, urine, and runs it through a series of filters, distillation units, and catalytic reactors, until what comes out the other side is water clean enough to drink. For years, the widely cited figure for this system's efficiency was around 90%, meaning that for every 10 units of water that went into the system, about 9 came back out as usable water. That already sounds remarkable. Astronauts have joked for years, with a mix of dark humor and genuine pride, that today's coffee is tomorrow's coffee, filtered through a system precise enough that the water coming out the other end is, by some measurements, cleaner than most municipal tap water on Earth. But 90% was not the ceiling. Engineers kept refining the system, replacing components, improving the brine processing that handles the leftover concentrated waste from distillation, and by the early 2020s, NASA announced that the system had pushed past 98% water recovery. Read that number again, because it is the number this entire episode pivots around. 98%. That means for every 100 units of water that enter the system as urine, sweat, breath moisture, and hygiene runoff, 98 of those units come back out as drinkable water. Only 2 units are lost. On the surface, that sounds like the problem is essentially solved. If you can recover 98% of your water indefinitely, you would think a sealed spacecraft could function almost forever, topping up that 2% loss from a stored reserve that could, in theory, last for years. And for water alone, in isolation, that is roughly true. A crew that started with even a modest reserve tank on top of what is already cycling through the station could stretch their water supply for a very long time before the 2% loss became the dominant problem. This is the first thing the thought experiment forces us to confront. The engineering triumph here is real. It is not an exaggeration to call a 98% closed water loop one of the great achievements of applied chemistry and mechanical engineering. Humans built a machine that does, in miniature, something close to what an entire planet's water cycle does for free. And yet, that 2% gap is not nothing. Over a single day, with a crew of 6, the losses are tiny, almost rounding error small. Over a year, those tiny losses add up to a measurable deficit. Over several years, sealed with no resupply, that deficit becomes the difference between a stored reserve that lasts and one that does not. The 2% does not vanish into nothing. Some of it is lost to leakage in seals and connectors that degrade over time. Some of it is lost when astronauts go on spacewalks, because the cooling systems in spacesuits use water that sublimates away into space and cannot be recovered. A single spacewalk lasting 6 to 8 hours can use up several pounds of water through this sublimation cooling process alone. Water that, once vented as vapor into vacuum, is gone as completely as if it had been poured directly out of an airlock. Some of it is lost when astronauts go on spacewalks, and some of it is locked into solid waste that the system cannot economically extract every last drop from. None of these losses are dramatic on their own. But a sealed spacecraft does not get to ignore small numbers, because small numbers, given enough time, are exactly what a sealed system runs out of first. Oxygen tells a similar story, and the two systems are tied together in a way that most people do not expect. The station does not carry massive tanks of breathable oxygen as its primary supply, the way a scuba diver carries a tank. Instead, it produces oxygen on demand, using a system called the Oxygen Generation System, which performs electrolysis on water, splitting H2O into hydrogen and oxygen using electrical current. The oxygen gets pushed into the cabin atmosphere for the crew to breathe. The hydrogen, historically, was simply vented overboard, lost to space. More recent systems try to capture that hydrogen and combine it with carbon dioxide in a separate reactor, called a Sabatier reactor, to produce more water and methane, recovering some of what would otherwise be lost. The point of walking through this chain is this: oxygen production on a modern spacecraft is fundamentally a water problem. As long as you have water, and as long as you have electrical power to run the electrolysis unit, you can produce breathable oxygen more or less indefinitely. This is why, when people imagine a sealed spacecraft and immediately picture the oxygen gauge ticking down to zero like a video game health bar, they are picturing the wrong system. On a station equipped like the one currently in orbit, with power available, oxygen is not the first thing that runs out. It is downstream of water, and water, as we just established, has a 98% recovery rate and a relatively forgiving 2% loss. Food is where the picture changes completely, because food is the one major consumable that current technology cannot meaningfully regenerate. There is no food recycling system on the space station. None. Every calorie a crew member eats has to be physically launched from Earth, packaged, stored, and consumed once. Most of that food falls into one of a few categories. Thermostabilized foods, which are heated to destroy microorganisms and sealed in pouches or cans, much like military field rations. Freeze-dried foods, which have had nearly all their water removed and require rehydration with the station's recycled water before eating, and a smaller category of irradiated meats, which use ionizing radiation rather than heat to extend shelf life while preserving texture. Each of these preservation methods was chosen specifically to maximize how long the food can sit in storage before it becomes unsafe or unpalatable, and each of them has its own characteristic shelf life, typically rated by NASA in the range of 12 to 18 months for many items under standard storage conditions, though some products are rated longer. NASA's planning figures put the combined daily mass requirement for food, water, and the packaging involved at around 11 pounds per crew member per day. Of that, food itself typically accounts for somewhere around 3 to 4 pounds per person per day once packaging is included, translating to a caloric intake that is carefully tailored to each astronaut's body size. Typically, somewhere in the range of 2,000 to 3,400 calories daily, depending on the individual and their workload. The station typically keeps somewhere around 6 months of food on hand for its crew, a buffer that exists specifically so that a delayed cargo launch does not become an emergency. 6 months sounds like a long time, and for its intended purpose, as a buffer against launch delays, it is. But 6 months is nowhere close to the kind of timescale we are talking about when we ask how long a sealed spacecraft could sustain life with zero resupply, forever, starting from whatever was on board at the moment the hatch closed. And this is where a real historical event becomes one of the most useful anchors in this entire story. In the year 2014 and into 2015, the International Space Station experienced something that, at the time, genuinely worried mission planners. 3 separate cargo resupply missions failed within roughly 8 months of each other. An Orbital Sciences Cygnus capsule on a mission designated Orb 3 was destroyed in a launch accident in October of 2014, when its Antares rocket failed seconds after liftoff. A Russian Progress spacecraft, Progress 59, failed to complete its mission in April of 2015 after the vehicle began spinning uncontrollably following separation from its launch vehicle, ultimately burning up in the atmosphere with its cargo never reaching the station. And then, in June of 2015, a SpaceX Falcon 9 rocket carrying a Dragon cargo capsule on the CRS-7 mission broke apart less than 3 minutes after launch from Cape Canaveral, destroying over 2,300 kilograms of supplies, including food, water filtration hardware, and a docking adapter that had to be rebuilt and reflown later. 3 failures, back to back to back, on a station that normally operates with roughly 6 months of food and water reserves. NASA confirmed at the time that the crew's supply margin had dropped from the usual 6 months down to about 4 months. A Russian Progress resupply mission, a few days after the Falcon 9 failure, was able to extend that margin by roughly 1 month, but for a window of time. The people running human space flight operations were genuinely calculating contingency timelines, asking how long the crew could remain safely on board if the failures continued, and at what point an emergency evacuation back to Earth would become necessary rather than optional. This episode is built around the same kind of calculation NASA was quietly running during that 2015 window, except stretched to its logical extreme. What if, instead of a 1-month extension arriving just in time, nothing ever arrived again? What if the hatch sealed, the supply lines simply stopped, and the only question left was, starting from whatever consumables happen to be on board, how long does the loop hold? To make this concrete, imagine a spacecraft larger than the current station, built specifically for long-duration missions, the kind of vessel that has been proposed for crewed missions toward Mars and beyond. Give it a crew of 4 to 6 people. Give it cargo hold stocked, not with 6 months of food, but with several years of food. Give it the same 98% water recovery loop, the same electrolysis-based oxygen system, and then seal it completely. No resupply ever again. This is the scenario. And the first instinct almost everyone has when presented with this scenario is to ask, how long until the air runs out? That instinct is not wrong to ask. It is just aimed at the wrong half of the air problem. Because air on a sealed spacecraft is not one system. It is 2 systems running in opposite directions, and one of them is in far better shape than the other. The first system is oxygen, the gas the crew needs to breathe in, and as we have already established, that system is tied to water, and water has a 98% recovery rate and a relatively slow leak. The second system is carbon dioxide, the gas the crew's own bodies produce with every single breath, 24 hours a day, without pause, without rest, for as long as anyone on board is alive, and removing that gas from the cabin atmosphere continuously, forever, with no resupply of the materials that do the removing, turns out to be a far more fragile proposition than producing oxygen ever was. This is the first domino. Not the one most people expect, but the one the engineering actually points to. And to understand why, we have to look at what happens inside a sealed room, breath by breath, when the thing removing carbon dioxide from the air starts to fall behind. Every human being on board this sealed spacecraft is, at every moment, doing something the spacecraft has to actively counteract. With every exhale, a crew member releases carbon dioxide into the cabin atmosphere, a byproduct of the basic metabolic process that keeps them alive. A resting adult exhales somewhere in the range of about 2 pounds of carbon dioxide per day, a figure that rises further during exercise, which matters here because, as we will return to later, exercise is not optional on a long-duration mission. For a crew of 6, baseline output alone is roughly 12 pounds of carbon dioxide entering the cabin air every single day, day after day, with no exceptions, no days off, no pause for maintenance. On Earth, this is a non-issue, because the atmosphere of an entire planet absorbs it instantly, dilutes it into insignificance, and plants spend their existence pulling carbon dioxide back out of the air in exchange for the oxygen we breathe. In a sealed spacecraft cabin, there is no planet to dilute it into. There is only the volume of the cabin itself, a fixed, finite space, and if nothing actively removes that carbon dioxide, its concentration in the air begins climbing immediately, and it does not stop climbing on its own. The normal concentration of carbon dioxide in Earth's atmosphere is famously low, hovering around 0.04%. Spacecraft cabins are designed to keep carbon dioxide levels well below that of a stuffy room, generally targeting concentrations far lower than what would ever be noticeable to a person breathing it. But research conducted both on the ground and in spaceflight has shown something uncomfortable. The human body and brain start showing measurable effects from elevated carbon dioxide at concentrations that are still, by everyday standards, quite low. A study, sometimes referred to as the COGFX study, examining office workers in environments with varying ventilation rates, found that cognitive performance across multiple domains, including the ability to use information for crisis response and strategic thinking, declined measurably. When carbon dioxide concentrations rose into the range of roughly 0.1 to 0.12%, levels that can occur in poorly ventilated rooms here on Earth without anyone noticing anything is wrong, beyond perhaps feeling a little foggy. Push the concentration higher into the range of around 0.5%, sustained over time, and the effects become more pronounced: headaches, lethargy, and a documented decline in the kind of complex reasoning that, in our sealed spacecraft scenario, the crew would need most, especially if they are simultaneously trying to manage a cascading systems failure. Push it higher still, toward and beyond 1%, and the effects escalate toward more severe symptoms: shortness of breath, increased heart rate, confusion. At concentrations in the range of several percent, sustained exposure becomes acutely dangerous, leading to disorientation, loss of consciousness, and eventually death, as the gas interferes with the body's ability to offload carbon dioxide from the bloodstream at all, a condition called hypercapnia. The reason this matters so much for our sealed spacecraft is that, unlike water, which has a slow, well-managed 2% loss rate, carbon dioxide is being actively, continuously produced by the very presence of living people at a rate that does not slow down, does not pause, and does not care how clever the rest of the life support system is. The only thing standing between a normal cabin atmosphere and a rising tide of carbon dioxide is a piece of equipment whose entire job is to grab carbon dioxide molecules out of the air and either destroy them, store them, or vent them away. And, on the modern space station, this job is handled primarily by a system with a name that, again, sounds almost mundane for something this critical: the Carbon Dioxide Removal Assembly, often referred to by its acronym CDRA. This system uses a material called zeolite, a kind of mineral with a porous structure that acts almost like a molecular sponge, absorbing carbon dioxide molecules out of the air that passes through it. Once a zeolite bed becomes saturated, full of absorbed carbon dioxide, the system heats that bed up, which causes it to release the carbon dioxide it has captured, and that released gas is then vented out into the vacuum of space. The bed, now empty again, swaps back into service to keep absorbing, while a second bed goes through its own heating and venting cycle. Two beds, alternating, regenerating themselves over and over, theoretically indefinitely, as long as the system has power to run the heaters and the mechanical valves keep functioning. On paper, this sounds like exactly the kind of closed loop we praise the water system for. And in many ways, it is just as impressive an engineering achievement. But there is a crucial difference, one that becomes the central pivot of this entire episode, and it is this. The carbon dioxide removal assembly is mechanically complex, has multiple moving parts, requires consistent electrical power, and, in the real-world operational history of the space station, has a documented track record of breaking down. This is not a theoretical concern. Over the station's operational history, the CDRA units have experienced repeated issues with their valves and check valves sticking or failing, problems with the air selector valve that directs flow between the two zeolite beds, and degradation of the desiccant beds that remove humidity from the air stream before it reaches the carbon dioxide absorbing zeolite, a step that is necessary because the zeolite's capacity to absorb carbon dioxide is reduced if the air passing through it is too humid. When one of these components fails, the station has historically relied on a combination of on-orbit repairs using spare components carried up specifically for this purpose, and on a second, independent CDRA unit located in a different module so that, if one fails entirely, the other can carry the full load while the first is repaired or while replacement parts are flown up on the next cargo mission. Every one of those repairs, every spare valve, every desiccant bed replacement comes from a stockpile and on a sealed spacecraft with no further cargo missions. That stockpile is the entire remaining lifespan of the system once its first set of components wears out. It is not a passive filter that simply sits there working forever. It is an active machine with valves, heaters, blowers, and sensors, all of which are subject to wear, all of which can fail, and all of which, in a sealed spacecraft with no spare parts, beyond what was loaded before the hatch closed, represent a finite resource in their own right. Every valve has a number of open-close cycles it can perform before it wears out. A single CDRA unit, cycling between its two beds every several minutes around the clock, performs tens of thousands of these cycles per year, which means that even a component rated for what sounds like an enormous number of cycles can reach the end of its rated life within a handful of years of continuous operation. Every heater element has a lifespan, heating the zeolite beds to temperatures well above the cabin's ambient temperature, typically into a range that would be measured at around 200 to 400 degrees Fahrenheit during the regeneration cycle, repeatedly for years. Every blower motor has bearings that will eventually degrade. None of these components recycle themselves the way water molecules cycle through a distillation unit. When a part wears out, it either gets replaced from a stock of spares, or the system it belongs to stops working as designed. This is precisely the kind of failure that has already happened, for real, in the actual operational history of human spaceflight, and the most famous example comes not from the space station at all, but from one of the most legendary survival stories in the history of crewed spaceflight. Apollo 13. In April of 1970, an oxygen tank explosion crippled the Apollo 13 service module, forcing the 3 astronauts on board to abandon the main spacecraft and crowd into the lunar module. A vehicle designed to support 2 people for about 2 days, now suddenly needing to support 3 people for roughly 4 days on the journey back to Earth. The lunar module's own carbon dioxide scrubbers, which used canisters of a chemical compound called lithium hydroxide, were designed for that smaller crew and shorter duration, and they began to run out. The command module had plenty of spare lithium hydroxide canisters, more than enough to cover the extra time and the extra person. But there was a problem. The command module's canisters were square, and the lunar module's scrubber system was designed to accept canisters that were round. The shapes did not fit. Engineers on the ground, working with what the astronauts had on board, designed an improvised adapter using materials available in the spacecraft: plastic bags, cardboard from a flight manual cover, and tape to jury-rig the square canisters into a configuration that could be forced into the round housing. The fix worked. Carbon dioxide levels, which had been climbing toward dangerous territory, came back down, and the crew survived. The reason this story matters here is not nostalgia. It is that lithium hydroxide canisters represent the other major category of carbon dioxide removal technology, distinct from the regenerable zeolite system used as the primary method on the modern station. Lithium hydroxide works through a straightforward chemical reaction. The compound chemically binds with carbon dioxide, converting it into lithium carbonate and water, permanently removing the carbon dioxide from the air. The catch is right there in the word permanently. Once a lithium hydroxide canister has absorbed as much carbon dioxide as its chemical capacity allows, it is finished. It cannot be heated up and reset the way a zeolite bed can. It is, in effect, a single-use consumable, exactly like food or stored water, except instead of being something the crew puts into their bodies, it is something the spacecraft uses up in the process of keeping the air breathable. A single canister, depending on its size and the number of people breathing in the cabin, might last on the order of a day or so per crew member before needing to be swapped out for a fresh one. On a sealed spacecraft carrying lithium hydroxide canisters as either a primary or backup carbon dioxide removal method, the math becomes brutally simple. Count the canisters in storage. Divide by the number needed per day for the size of the crew, and that number, not some vague sense of the air running out, is one of the hardest, most concrete deadlines on the entire ship. Now place these two systems side by side, the way the spacecraft itself has to. On one side, you have the regenerable zeolite-based system, theoretically capable of running for as long as it has power, and as long as its mechanical components do not fail, but with a real-world history of breakdowns, requiring spare parts that, on a sealed ship, exist only in finite quantity. On the other side, you have lithium hydroxide canisters, mechanically simple, requiring no power and no moving parts, but absolutely finite, consumed permanently with every use, with a stockpile that can be counted, divided, and depleted on a schedule that can be calculated almost to the day. A well-designed, long-duration spacecraft would carry both, using the regenerable system as the primary method for as long as it functions, with the lithium hydroxide canisters held in reserve as a backup for exactly the kind of crisis Apollo 13 faced. But in our sealed forever scenario, backup takes on a different meaning. It is not a backup for a few days until the next resupply. It is the last line of defense, with nothing behind it, and a stockpile that, no matter how large, has a number on it. This is the moment where the thought experiment stops being abstract and starts becoming a genuine calculation, the kind scientists actually run when modeling long-duration mission survivability. If the regenerable carbon dioxide removal system functions perfectly, drawing on spare parts for repairs as components wear out, it can theoretically extend its operational life for years. The exact number depending entirely on how many spare valves, heaters, and blower assemblies were loaded before the hatch sealed. Every repair buys more time, but every repair also draws down a finite stock of spares that, unlike water, cannot be regenerated by any process on board. Eventually, whether after one repair or after dozens, the system will fail in a way that the available spares cannot fix. At that point, the spacecraft drops to its lithium hydroxide reserve, and the countdown becomes brutally linear. A fixed number of canisters, a fixed consumption rate per crew member per day, and a hard stop at the end of it. Once that stop arrives, carbon dioxide concentration in the cabin begins climbing at a rate determined by crew size and cabin volume, with no mechanism left to pull it back down, moving through the zone of headaches and cognitive impairment, then through the zone of confusion and rising heart rate, and finally into the zone where the body can no longer offload carbon dioxide from the blood fast enough to sustain consciousness. What makes this particular failure mode so unsettling, more than any single number in the calculation, is the timing of its consequences relative to everything else happening on the ship. Rising carbon dioxide does not wait politely for the crew to finish dealing with whatever caused the regenerable system to fail in the first place. It begins its slow climb the moment removal capacity falls behind production, and its first effects, the headaches, the fog, the subtle decline in the ability to think through a complex mechanical problem, arrive precisely when the crew most needs their full cognitive faculties to diagnose the failure, locate the right spare parts, and execute the repair correctly under pressure. A crew working with perfectly clear heads might fix a failing valve in an hour. The same crew, several days into a slow carbon dioxide creep, working through the early stages of hypercapnia, without even realizing that is what is happening to them, might take twice as long, made twice as many small mistakes, and used up margin they did not know they were spending. There is one more layer to this that rarely gets discussed, and it concerns the desiccant beds mentioned earlier, the components that strip humidity out of the air before it reaches the zeolite. Humans are remarkably effective humidifiers without trying to be. Between breathing, sweating, and the water vapor released during cooking and hygiene activities, a crew of 6 can add several pounds of water vapor into the cabin air every day. The air conditioning and humidity control systems that pull this moisture back out are part of the same overall thermal and atmospheric control architecture as the carbon dioxide removal system, sharing some of the same air handling pathways, the same fans, and in some configurations, components that serve double duty. If humidity control degrades at the same time carbon dioxide removal is struggling, the zeolite beds become less effective at exactly the moment they can least afford it, because moisture-saturated zeolite has reduced capacity to bind carbon dioxide molecules. This is the first thread connecting the mechanical countdown to the human one, and it is a thread that will reappear in different forms throughout the rest of this story. The spacecraft's systems and the bodies of the people inside it are not two separate problems running on two separate clocks. They are coupled, and a slow leak in one can quietly accelerate the failure of the other, long before anyone on board fully understands what is happening to the numbers on the wall display, or to the numbers running through their own bloodstream. Carbon dioxide is not the only thing a sealed spacecraft has to fight continuously, and it is not the only system where a small, almost invisible percentage point determines everything. While the crew is dealing with the slow arithmetic of canisters and zeolite beds, a second, quieter cascade is unfolding in parallel, one that started the moment the hatch sealed and has been running ever since, completely unnoticed, because for the first months and even years, it produces no symptoms at all. This is the cascade hidden inside the water recovery system, and it is, in some ways, more unsettling than the carbon dioxide problem because it does not announce itself with headaches or fog. It simply, quietly, drifts. Remember the number from earlier, 98%. That figure represents the water recovery system operating at its best, with every filter, membrane, and reactor performing at the specification it was designed for. The component most responsible for pushing the recovery rate from the older 90% figure up to that 98% figure is a relatively recent addition called the brine processor assembly, which was delivered to the station and brought into operation in the early 2020s as the final piece of what NASA had been calling, for years, a nearly closed-loop water system. To understand what this machine does, you have to understand what happens to urine once it enters the recycling system. The primary distillation process, handled by a component called the urine processor assembly, pulls most of the water out of urine, but it leaves behind a concentrated leftover liquid called brine, a thick, mineral-heavy residue that, for years, was simply treated as waste, collected in containers, and eventually discarded along with other trash. The brine processor assembly was built specifically to take that leftover brine and squeeze even more water out of it, using a combination of warm, dry air passed through a flexible membrane contactor, drawing residual water vapor out of the brine and into the airstream, which is then run back through the main system to be condensed and purified like any other water vapor source. This is the difference between 90% and 98%. It is the difference between treating the leftovers as garbage and treating them as one more ingredient. Here is the problem with squeezing the absolute last drops of water out of anything. The thing doing the squeezing wears out fastest. The membrane contactor inside the brine processor assembly is, by its nature, working with the most concentrated, mineral-saturated, chemically aggressive liquid in the entire water system. Salts and minerals that were dissolved in the original wastewater become concentrated in the brine precisely because most of the water has already been removed from it. As that brine is processed again and again, mineral deposits build up on the surfaces of the membrane, gradually reducing how efficiently water vapor can pass through it. On a station that receives periodic resupply, this is a manageable maintenance item. When the membrane's performance degrades past a certain point, a replacement cartridge is loaded into the assembly during the next cargo delivery, and the recovery rate returns to its 98% baseline. On a sealed spacecraft with no resupply, every replacement cartridge comes from a finite stockpile loaded before departure, and once that stockpile is exhausted, the membrane keeps degrading, with no way to reset it. This is where the quiet drift begins. As the brine processor's membrane degrades and no replacement is available, its contribution to overall water recovery does not collapse all at once. It fades. The system does not suddenly drop from 98% to some catastrophic low number. Instead, the recovery rate slides gradually back toward the baseline that existed before this component was added, somewhere in the range of 90 to 93%. As the rest of the water recovery system, the distillation units, the filter beds, the catalytic reactors, continue operating largely as designed, because those components are less exposed to the harshest, most concentrated waste streams and degrade far more slowly. A drop from a 2% loss rate to something closer to a 7 to 10% loss rate sounds, on a daily basis, almost meaningless. A crew of 6 losing 2% of their water cycle per day versus losing 8% of their water cycle per day is a difference measured in a handful of liters. But remember, this is a sealed system with a finite stored reserve acting as the buffer against any loss rate above zero. A loss rate that quadruples does not just slightly shorten the timeline calculated from the original 2% figure. It can cut that timeline by a factor of 3 or 4, compressing what might have been a multi-year buffer into a window measured in a single year, or less, depending on how large the stored reserve was to begin with, and how early in the mission the brine processor's membrane begins to fail. And the water system does not exist in isolation any more than the carbon dioxide system did. Remember that oxygen production through electrolysis depends on having water to split into hydrogen and oxygen. A water recovery system sliding from 98% down toward 90% does not just mean less drinking water for the crew. It means less feedstock for the oxygen generation system, which means either drawing down a separate stored oxygen reserve faster than planned, or reducing the margin of breathable oxygen available in the cabin atmosphere at exactly the same time the carbon dioxide removal system may be experiencing its own degradation. Two systems, each with their own slow leak, each invisible day to day, each quietly accelerating the other's timeline. This is the nature of a truly sealed environment. Nothing fails in isolation because every system was designed assuming the others would keep functioning at their rated specifications, and a sealed spacecraft is, by definition, a place where nothing gets to stay at its rated specification forever. While the water system drifts, a second and far less subtle problem accumulates in plain sight: solid waste. Unlike water, which has an entire recovery architecture built around it, solid human waste, feces, used hygiene wipes, worn-out clothing, food packaging, has essentially no recovery pathway at all on current spacecraft. On the space station today, this waste is collected, sealed into bags, packed into cargo vehicles that have already delivered their supplies, and disposed of by allowing those vehicles to burn up during re-entry into Earth's atmosphere. A process that effectively turns visiting cargo ships into a one-way garbage truck. On a sealed spacecraft with no cargo ships ever arriving or departing, this disposal pathway simply does not exist. Every bag of solid waste generated by the crew for the entire duration of the mission has to be stored somewhere on board, permanently taking up volume that was either designed into the spacecraft from the beginning as dedicated waste storage, or that gets carved out of space originally intended for something else as the mission stretches on. For a crew of 6, even a conservative estimate of solid waste and discarded packaging accumulating at a rate of a few pounds per person per day adds up over a single year to a mass measured in thousands of pounds, and a volume that, depending on how tightly it can be compacted, could realistically come to occupy the equivalent of an entire small room's worth of storage by the end of just the first year alone, with that room growing larger every year after. The volume problem is real, but it is not, by itself, the most pressing issue. The more pressing issue is biological. Stored human waste is not inert. It contains living microorganisms, and in a sealed environment with controlled temperature and humidity, those microorganisms do not simply die off and disappear. Depending on how waste is stored, whether it is desiccated, chemically treated, or simply bagged and sealed, Microbial activity can continue at some level for extended periods, producing gases as a byproduct of that activity. Gases that can include compounds responsible for unpleasant odors, but more importantly, gases that represent one more small continuous input into the cabin atmosphere that the air management systems have to handle. A spacecraft's atmospheric processing is designed around the expected outputs of a healthy crew breathing and the expected outputs of its own equipment. It is not necessarily designed around the long-term outgassing of an ever-growing, ever-aging accumulation of biological waste that, on a normal mission, would have been jettisoned within weeks of being generated. Over months and years, this becomes one more slow contributor to the overall air quality challenge, layering on top of the carbon dioxide story from earlier, a background hum of additional trace contaminants that the same limited filtration capacity has to absorb, on top of everything else it is already struggling to keep up with. Now, turn to food, because food is where the arithmetic becomes the most stark. Precisely because food is the one major system with no recovery loop of any kind. Every other system we have discussed, air, water, even to some extent power, involves some form of regeneration, some attempt to take an output and turn it back into an input. Food does not. A calorie eaten is a calorie gone. There is no equivalent of the brine processor assembly for a ration pack. This means that, unlike water, where the question is about a slowly drifting loss rate, the question for food is brutally simple. How much was loaded before the hatch sealed? How much does the crew consume per day? And does the supply outlast everything else? Or does it run out first? Using the figures we established earlier, a crew member consumes somewhere in the range of 3 to 4 pounds of food and packaging per day, supporting a caloric intake typically in the range of 2,000 to 3,400 calories, depending on body size and activity level. For a crew of 6, that works out to somewhere around 20 pounds of food consumed per day, or roughly 7,000 pounds per year. For the crew as a whole, a normal station resupply cycle keeps something on the order of 6 months of food on hand, which for a crew of 6 would represent somewhere in the neighborhood of 3,500 pounds of stored food at any given time. For our hypothetical sealed long-duration spacecraft, built specifically for a mission with no resupply, mission planners would load vastly more than 6 months. If such a spacecraft were stocked with, say, 5 years of food for a crew of 6, that represents somewhere in the range of 35,000 pounds of food, occupying a volume that becomes one of the largest single mass allocations on the entire vehicle, larger than most of the life support hardware combined. This is not a trivial design constraint. Every additional year of food stored is mass that has to be launched, mass that affects the spacecraft's propulsion requirements, and volume that competes with crew quarters, laboratory space, and the equipment needed to keep everyone alive in other ways. But even setting aside the engineering challenge of simply carrying that much food, there is a second problem hiding inside the food question, one that has nothing to do with running out of calories and everything to do with what happens to food while it sits in storage for years. Spacecraft food is overwhelmingly freeze-dried, dehydrated, or thermostabilized, processes chosen specifically because they extend shelf life far beyond what fresh food could achieve. Even so, that shelf life is not infinite, and it is not uniform across every nutrient in the food. Studies conducted on stored spaceflight food, looking specifically at multi-year storage scenarios relevant to missions toward Mars, have found that while the caloric content and basic macronutrients The proteins, fats, and carbohydrates remain largely stable over several years. Certain vitamins degrade significantly faster. Vitamin C, in particular, has been documented to degrade substantially within the first 1 to 2 years of storage in some spaceflight food items, with thiamine and vitamin A showing their own, somewhat slower, but still measurable decline curves over similar time frames. The caloric math might say a 5-year food supply provides 5 years of energy, and that part of the math would be correct. But a crew member eating food that still provides adequate calories while slowly losing its vitamin content is not eating the same diet they started with. They are, gradually, year over year, sliding toward a diet that technically satisfies their energy requirements while becoming progressively deficient in specific micronutrients, an effect that, on its own, produces no immediate symptoms, but that compounds, quietly, alongside everything else, contributing over months and years to weakened immune function, slower wound healing, and reduced resilience against every other stressor this story has already described. Power is the fourth thread, and in many ways, it is the thread that ties every other system together. Because every system we have discussed so far, the carbon dioxide removal assemblies, heaters and valves, the water recovery system's pumps, and the brine processor's air heaters, the oxygen generation system's electrolysis unit, even the basic fans that circulate cabin air so that carbon dioxide does not pool in stagnant pockets near a sleeping crew member's face. All of it runs on electricity. A spacecraft's power system typically combines large solar panel arrays with battery banks that store energy for use during the portions of an orbit or a deep space trajectory when the panels are not optimally oriented toward the sun. The current space station, for reference, is powered by a set of large solar array wings, and in recent years, a portion of its original nickel-hydrogen batteries have been replaced with newer lithium-ion battery units, a switch made specifically because lithium-ion batteries offer a better ratio of stored energy to mass and volume, an important consideration for any spacecraft where every pound matters. Solar panels degrade over time, and this is not a maintenance issue that can be fixed with a spare part. It is a fundamental consequence of operating in the space radiation environment, the same energetic particles that make up the radiation environment of space. The subject we will turn to fully in a moment also gradually damage the semiconductor materials inside solar cells, reducing their efficiency at converting sunlight into electricity. Documented degradation rates for solar arrays in orbit typically fall in the range of about 1 to 3% of capacity lost per year, depending on the specific technology and the radiation environment the spacecraft operates in. On a mission lasting a handful of years, this sounds almost negligible, a single-digit percentage shaved off the top of the power budget. But stretch the timeline out the way our sealed spacecraft scenario demands, and that 1 to 3% per year compounds. After 10 years, even at the lower end of that range, a solar array could be operating at somewhere around 90% of its original capacity. After 20 years, depending on the rate, that figure could be approaching 75 to 80%, or lower at the higher end of typical degradation rates. The batteries that store and buffer this power have their own separate aging process, with lithium-ion battery systems experiencing capacity loss with every charge and discharge cycle, an effect familiar to anyone who has owned a smartphone for several years and noticed it no longer holds a charge the way it once did. An effect that becomes more pronounced over thousands of cycles, which, for a spacecraft completing an orbit every 90 minutes or running continuous charge-discharge cycles over years, accumulates far faster in absolute cycle count than it would for almost any application on Earth. A power system operating at 80% of its original capacity does not mean the spacecraft simply runs everything at 80% effectiveness, evenly, forever. It means mission planners, or, in our scenario, the crew themselves, eventually face choices about what gets power and what does not. Every system we have discussed has a power draw associated with it, and every one of those power draws was calculated against the power budget the spacecraft had when it launched, not the power budget it has after a decade or two of solar panel degradation and battery aging. A carbon dioxide removal assembly that requires a certain amount of power to run its heaters during the regeneration cycle does not become more efficient because the ship has less power available. It simply requires the same amount of power from a smaller total pool, meaning something else has to be reduced or turned off to compensate. The same is true for the oxygen generation system's electrolysis unit, for the water recovery system's pumps, and the brine processor's air heaters, for cabin lighting, for the equipment astronauts use to exercise against bone and muscle loss, a subject we are about to turn to in detail. A declining power budget does not cause one dramatic failure. It causes a slow-motion triage, where the crew, or the automated systems managing the ship, begin making trade-offs between systems that were never designed to be traded off against each other, because they were never all expected to be drawing on a power supply that had quietly shrunk by 10, 15, 20% from where it started. Now we can begin to assemble these threads into something resembling an actual answer, though it has to be presented honestly, as the range it genuinely is, rather than the single dramatic number people often expect. If we imagine our hypothetical sealed spacecraft, crew of 6, carrying roughly 5 years of food, equipped with the 98% water recovery system and a substantial stockpile of spare parts and lithium hydroxide canisters for the carbon dioxide removal system, several distinct clocks are running simultaneously from the moment the hatch seals. The carbon dioxide removal system's spare parts inventory, combined with its lithium hydroxide reserve, might realistically extend functional carbon dioxide control somewhere in the range of several years to perhaps a decade or more, depending heavily on how many spares were loaded and how often the regenerable system requires intervention. The water recovery system's brine processor, once its membrane stockpile is exhausted, causes the overall recovery rate to drift from 98% down toward the 90 to 93% range, a shift that, combined with a stored water reserve, might extend the water supply for a period that could realistically range from several years to well over a decade, again depending on the size of the initial reserve. Food, with no recovery loop at all, provides a hard ceiling defined entirely by however many years' worth was loaded. In our example, 5 years, though the nutritional quality of that food, particularly its vitamin content, begins meaningfully declining well before the calories run out. And power, declining at somewhere between 1 and 3% per year, begins forcing trade-offs between these other systems on a timeline measured in years to decades, with the exact point at which those trade-offs become unsurvivable depending on how the crew or the ship's automated systems choose to prioritize. Put all of this together, and a calculated, honest range begins to emerge. For a spacecraft stocked the way we have described, with 5 years of food as the anchor point, the combination of food running low, water recovery degrading, and power declining enough to force impossible trade-offs between carbon dioxide control and oxygen production points toward a survivable window that, in the most optimistic combination of these factors, might stretch toward the upper end of that 5-year food supply, perhaps even slightly beyond it, if rationing begins early enough and water reserves were generous. In the most pessimistic combination, where the brine processor's membrane degrades early, where the carbon dioxide removal system requires more repairs than spares allow, and where power degradation forces hard choices sooner rather than later, that window could close significantly earlier, potentially years before the food itself would have run out, with the mechanical and chemical systems becoming the limiting factor rather than the pantry. Either way, the number that ends this story will not be a single mechanical failure on a single day. It will be the point at which these overlapping curves, food, water recovery efficiency, carbon dioxide control capacity, and available power, cross a threshold the crew can no longer manage simultaneously. And here is the detail that makes everything we have discussed so far only half of the real picture. Every calculation we have just walked through assumes the spacecraft's machinery is the thing with a clock running on it, and that the crew themselves are a constant, a fixed set of people, consuming a fixed amount of resources, producing a fixed amount of carbon dioxide and waste, for as long as the equipment can support them. That assumption is wrong, and it is wrong in a way that becomes more important the longer the timeline stretches. The human body, sealed inside that same spacecraft, breathing that same air, drinking that same recycled water, is not a fixed, unchanging consumer of resources. It is itself a system, with its own degradation curves, its own slow leaks, and its own thresholds, running on timelines that, in some cases, move faster than anything we have discussed about the machinery itself. The ship has clocks, so do the people inside it. And to understand the true answer to how long anyone could actually survive in a sealed spacecraft, we have to stop looking at the walls and start looking at the crew. The moment a spacecraft leaves the protective cocoon of Earth's magnetic field and thick atmosphere, every person on board begins absorbing radiation at a rate that, on Earth, would be considered remarkable, and in deep space, is simply the baseline. Earth's magnetic field deflects the majority of charged particles streaming from the Sun and from deep space, and the atmosphere absorbs much of what gets through. The International Space Station, orbiting within the protective bubble of that magnetic field, still exposes its crew to meaningfully elevated radiation compared to the surface of the Earth. But a spacecraft sealed and traveling beyond that bubble, the kind of vessel our scenario describes, loses that shielding almost entirely, leaving only whatever shielding the spacecraft's own hull and contents provide. Two main sources contribute to this exposure. The first is galactic cosmic radiation, a constant, low-level rain of high-energy particles originating from outside our solar system, the remnants of ancient supernova explosions and other violent cosmic events that travels through space in essentially every direction, at every moment, indefinitely. This background radiation cannot be avoided by timing or trajectory. It is simply always present, a permanent feature of the deep space environment. The second source is solar particle events, sudden, intense bursts of charged particles released by the Sun during solar flares and coronal mass ejections, which are unpredictable, can arrive with little warning, and can deliver an enormous radiation dose in a very short period, far exceeding the background rate from galactic cosmic radiation during the event itself. Direct measurements of this environment have already been taken on the way to Mars, not by humans, but by an instrument called the Radiation Assessment Detector, carried aboard the spacecraft that delivered the Curiosity rover to the Martian surface. During that roughly 8-month cruise, this detector recorded the radiation dose that a human traveler would have absorbed, and the results confirmed what theoretical models had predicted. The dose rate in deep space, shielded only by a typical spacecraft hull, is significantly higher than what is experienced aboard the space station, and a round trip to Mars using similar transit times would expose a crew member to a substantial fraction of their entire career radiation limit from transit time alone, before any time spent on the Martian surface is even factored in. NASA's career radiation exposure limits for astronauts are based on cumulative dose, measured in units called millisieverts, and are calibrated to keep an astronaut's lifetime increased risk of fatal cancer from radiation exposure below a certain threshold, with the exact limit varying based on factors including the astronaut's age and biological sex, since younger individuals and women have, according to the epidemiological data NASA uses, a statistically higher lifetime cancer risk per unit of radiation exposure due to the longer remaining lifespan over which that risk can manifest, and due to certain radiation-sensitive tissues. These limits are typically cited in the range of somewhere around 600 millisieverts of cumulative effective dose over an astronaut's career, though the precise figure depends on the individual. For comparison, a single chest X-ray on Earth delivers a dose on the order of 1/10 of a millisievert, meaning the career limit represents a dose roughly equivalent to several thousand chest X-rays, a number that puts into perspective just how much radiation a multi-year deep space mission accumulates compared to anything experienced in a normal medical setting on Earth. Now, stretch that same exposure rate across a sealed spacecraft scenario lasting not 2 to 3 years, but potentially a decade or more. The galactic cosmic radiation background does not pause, does not lessen with time, and accumulates linearly, year after year, with no biological reset button. A crew exposed to a dose rate that would consume a meaningful fraction of their career limit over a 2 to 3 year Mars mission would, over a 10-year sealed mission, accumulate a dose that could exceed established career limits by a significant margin well before any of the mechanical systems we discussed reach their own breaking points. The health consequences of cumulative radiation exposure at these levels are not limited to an elevated long-term cancer risk, though that risk is real and well documented. Research using ground-based particle accelerators that simulate the heavy ion component of galactic cosmic radiation has found evidence that this specific type of radiation, distinct from the more common forms of radiation encountered on Earth, can produce changes in brain tissue at a cellular level, with studies in animal models showing effects on cognition, memory, and decision-making following exposure to galactic cosmic radiation-like particle doses. While the translation of these animal studies directly to human spaceflight timelines remains an active area of research, with significant uncertainty about exact thresholds and effects in humans over multi-year exposures, the existence of this research means that radiation in our sealed spacecraft scenario is not simply a long-term cancer statistic to be worried about decades later. It is a potential contributor to cognitive decline within the mission itself, layering on top of and potentially compounding the carbon dioxide-related cognitive effects we discussed earlier, two entirely separate mechanisms, one chemical and one radiological, both potentially eroding the same thing, the crew's ability to think clearly enough to keep managing everything else. Radiation is not the only thing the human body loses in space, and it is not even the most immediate. From the moment a person enters microgravity, their body begins responding to the absence of the constant load that gravity normally places on bones and muscles. On Earth, the skeleton is under continuous mechanical stress. Every step, every time someone sits up or lifts something, sending signals to bone tissue that maintain its density. In microgravity, that stress essentially disappears, and the body responds the way it would to any unused tissue. It begins breaking it down. Documented bone density loss in astronauts on long-duration missions occurs primarily in weight-bearing bones, the hips, the spine, the legs, at rates that have been measured in various studies at roughly 1 to 1.5% of bone mineral density per month in regions most affected during the early months of a mission, though the rate can vary by individual and by skeletal site, and tends to be most pronounced before any adaptation or countermeasure effects stabilize it somewhat. Muscle mass follows a similar pattern, particularly in the muscles most involved in standing, walking, and maintaining posture against gravity, muscles that, in microgravity, are, essentially, never used for their primary function. The standard countermeasure used on the space station today is exercise, specifically resistance exercise, designed to load the skeleton and muscles in ways that mimic, as closely as possible, the loads they would experience on Earth. Astronauts on long-duration missions typically spend around 2 hours per day on dedicated exercise using specialized equipment, including a treadmill with a harness system that pulls the astronaut down against the running surface to simulate body weight, and a resistance exercise device that uses vacuum cylinders to provide a load for weightlifting-style exercises. In some cases, this exercise regimen is supplemented with medications from a class of drugs called bisphosphonates, originally developed to treat osteoporosis on Earth, which have been studied as a way to further reduce bone density loss during spaceflight by slowing the rate at which bone tissue is broken down. This countermeasure significantly reduces, but does not entirely eliminate, bone and muscle loss, even with rigorous daily adherence. And here is where this thread connects back to everything we have already discussed, that exercise equipment is itself machinery, with moving parts, belts, cables, and vacuum seals that wear out over time, requiring maintenance and occasionally replacement parts. Drawing on the same finite stockpile of spares as every other system on the ship, and requiring power from the same declining power budget we discussed earlier. A treadmill belt that wears through, or a resistance device whose vacuum cylinders lose their seal on a station with regular resupply, gets replaced. On a sealed spacecraft, a failure of the primary exercise countermeasure equipment, years into a mission, does not just inconvenience the crew, it removes or degrades the single most effective tool they have for slowing down a process, bone and muscle loss, that has already been running continuously since the day they left Earth, and that does not pause just because the equipment used to fight it has broken down. And if medication stockpiles, including any bisphosphonates carried for this purpose, are also finite and not resupplied, that secondary layer of protection has its own depletion date as well, one more buffer with a bottom to it. Beyond bone and muscle, the cardiovascular system adapts to microgravity in ways that create their own long-term concerns. On Earth, the heart and blood vessels work continuously against gravity to keep blood properly distributed throughout the body, particularly to push blood up from the legs back toward the heart and brain. In microgravity, this gravitational gradient disappears, and fluid that would normally pool in the lower body redistributes toward the head and upper body, an effect astronauts notice almost immediately as a kind of persistent fullness in the face and sinuses. Over the long term, this fluid shift has been linked to a condition that has become one of the more significant concerns identified through long-duration spaceflight research, generally referred to as spaceflight-associated neuroocular syndrome, in which sustained pressure changes around the optic nerve and eye are associated with structural changes to the eye itself, including flattening of the back of the eyeball and swelling of the optic nerve, changes that have been documented to cause measurable, and in some cases lasting, alterations to astronauts' vision following long-duration missions. NASA's own twin study, which compared one astronaut who spent nearly a year aboard the space station with his identical twin who remained on Earth, found a range of biological changes during the mission, including alterations in gene expression patterns, changes in the length of structures called telomeres located at the ends of chromosomes, which are often associated with cellular aging, and shifts in the gut microbiome, many of which return toward pre-flight levels after the astronaut returned to Earth, but some of which, including certain gene expression changes, persisted for months afterward. The exact long-term trajectory of these eye and cellular changes over missions lasting many years beyond anything yet flown remains, by necessity, an area where direct data does not exist. But the documented progression of these changes over missions of 6 months to a year provides no indication that the underlying mechanism, the altered fluid distribution and cellular stress caused by the absence of gravity, would simply stop progressing on a longer mission. If anything, the available evidence points toward these structural and cellular changes continuing to develop for as long as the underlying cause, microgravity itself, remains present, which on a sealed spacecraft is to say, forever. All of these physical changes, radiation exposure, bone and muscle loss, cardiovascular and ocular changes, occur regardless of how the crew feels about their situation, how well they get along with each other, or how their minds are coping with the isolation. But the human mind is not a passive bystander in any of this, and the psychological dimension of long-duration isolation has been studied directly through analog missions, specifically designed to simulate the experience of a long-duration spaceflight without actually leaving Earth. The most extensive of these was a study called Mars 500, conducted in Russia, in which a crew of 6 volunteers spent 520 days, just over 17 months, sealed inside a mock spacecraft facility, with no physical contact with the outside world beyond communications, deliberately delayed to simulate the time lag of a real Mars mission. Researchers monitoring the crew throughout that mission documented measurable changes in sleep patterns, with several crew members shifting toward longer sleep durations and altered sleep timing as the mission progressed, alongside reductions in physical activity levels compared to the mission's early phases, changes that researchers linked to a kind of behavioral conservation, as if the body and mind were, without conscious decision, beginning to economize on effort the longer the isolation continued. Another major analog program, called High Seas, conducted in Hawaii, ran multiple missions with crews isolated for durations of up to a year, in a habitat designed to simulate the conditions of a Mars surface mission, and similarly documented fluctuations in crew cohesion and mood across different mission phases. The findings from these studies, and from decades of research into isolated and confined environments more broadly, including research conducted on Antarctic Research Station crews, who experienced their own form of extended isolation during the winter months when resupply and evacuation become impossible, consistently identify a pattern that researchers sometimes refer to as the third quarter phenomenon. Crews on long-duration isolated missions tend to maintain relatively stable mood and morale during the first portion of the mission, while the novelty and sense of purpose remain strong, and during the final portion, as the end becomes visible and motivation returns. It is during the middle portion, roughly the third quarter of the mission's total duration, where documented declines in mood, increased irritability, sleep disturbances, and interpersonal friction tend to peak. For a mission lasting weeks or months, this third quarter dip, while real and significant, is something crews have generally been able to work through, supported by communication with family, by ground-based psychological support teams, and simply by the knowledge that the mission has a defined end date that is, eventually, getting closer. A sealed spacecraft, in our scenario, has no such end date and, crucially, no communication with anyone outside the ship, because there is no outside to communicate with in any meaningful sense. No ground-based support team, no family voices, nothing. The third quarter phenomenon, as documented in missions with a defined, finite length, may not even be the correct framework for a mission where the crew does not know, and cannot know, how long they will ultimately be expected to endure, since the actual endpoint is not a calendar date, but whichever of the mechanical thresholds we discussed throughout this story arrives first. A threshold the crew themselves may be actively trying to calculate and recalculate as new information about their own system's degradation becomes available. The psychological burden of living inside a structure whose remaining lifespan is itself an open, shifting, and deeply consequential question, recalculated every time a piece of equipment fails or a spare part inventory runs lower than expected, represents a form of sustained uncertainty that no analog mission conducted on Earth, with its guaranteed exit and guaranteed eventual rescue, has ever truly replicated. This is the point where every thread we have followed throughout this entire story converges. The carbon dioxide removal system, with its finite spares and its lithium hydroxide reserve. The water recovery system, with its slowly degrading brine processor and its drifting recovery rate. The food supply, with its hard sealing and its slowly fading nutritional content. The power system, with its 1 to 3% annual decline, forcing trade-offs between systems that were never meant to compete for the same shrinking pool of electricity. And now, layered on top of all of it, the crew themselves, bodies losing bone density and muscle mass month over month, eyes slowly changing shape under the redistribution of fluid that gravity used to manage, cellular changes detected at the genetic level that linger long after any return to Earth, minds absorbing a steady accumulation of radiation whose cognitive effects, research suggests, may compound the same kind of impairment that rising carbon dioxide produces, and a psychological landscape with no precedent, no defined endpoint, and no outside world to provide perspective, support, or relief. The honest answer to the question this entire episode set out to answer is not a single number, and it was never going to be. It is a convergence point, the moment where several independent curves, the mechanical ones measured in spare parts and recovery percentages, and the biological ones measured in bone density and cognitive performance, cross thresholds that, individually, might each be survivable, but that, together, overwhelm a crew's ability to keep functioning. Based on the figures we have walked through, for a well-stocked, well-designed spacecraft of the kind that does not yet exist, but that current technology could plausibly build, that convergence point most likely falls somewhere in a range, stretching from several years to perhaps a decade or slightly more, with the exact position within that range determined less by any single dramatic failure, and more by which of these slow, quiet, compounding curves happens to bend first, and how the crew chooses to respond when it does. What makes this answer genuinely grim is not the number itself, it is what the number represents. Every system described in this episode, the 98% water recovery, the regenerable carbon dioxide scrubbers, the electrolysis-based oxygen generation, represents decades of engineering effort, billions of dollars of investment, and some of the most sophisticated applied chemistry and mechanical design human civilization has ever produced. And the best version of all of that, combined together, sealed inside the most advanced spacecraft we could plausibly build with current technology, still produces a survival window measured in years, not decades, not centuries, and certainly not the indefinite, self-sustaining permanence that would be required for humanity to live somewhere other than where it currently lives, without that place eventually requiring resupply from somewhere else. Which brings this story back to the place it started, 250 miles below where this entire thought experiment began. Every single system described tonight, the water recycling, the oxygen generation, the carbon dioxide scrubbing, the food production, exists in a far larger, far older, far more capable form. All around you, right now, the planet beneath you recycles water through an entire global cycle of evaporation, condensation, and rainfall, at a scale so vast that human water consumption barely registers as a rounding error. Plants and oceans process carbon dioxide and produce oxygen at a scale that has kept the atmosphere in a survivable balance for the entire history of complex life. Soil and ecosystems break down waste and return it to the cycle in forms that feed the next generation of life, indefinitely, without anyone monitoring a brine processor's membrane or counting lithium hydroxide canisters. Every spacecraft life support system humanity has ever built, including the most advanced ones described in this episode, is, in the end, an attempt to recreate, in miniature, mechanically, imperfectly, and for a finite time, something that the Earth does completely, biologically, and so far, for as long as anyone has been alive to notice. We spend a great deal of effort imagining what it would take to survive somewhere else. And the honest answer, the one the engineering keeps quietly pointing toward, is that we are already living inside the only version of this system that has ever actually worked without an expiration date. And most of us will go to sleep tonight without ever thinking about it at all. Sleep gently, traveler. The only true ark you have ever needed is the one beneath you,